Okay, so we're talking more about uniform circular motion, and I wanted to give these two equations which we can use for velocity, r omega, and acceleration, which is v squared over r. I also try to draw a little bit of a picture here. Just imagine a car or whatever going in a circle. This dashed line is the velocity. That's where the object wants to go, because the object wants to stay in motion. It doesn't want to change our velocity directions. That's your tangential velocity. Our acceleration, our centripetal acceleration, is center seeking, and it points to the center. And then r is just the distance from the center to any point on the circle. So we have all these, and essentially what we're going to end up doing, we're going to talk a little bit more, maybe do some problems here. But your goal is to go through your knowns, your unknowns, look at your equations, possibly use Newton's second law, and work through some of them. So hopefully these equations are enough to get us started, and we can maybe get into some problems here. So let's imagine, let's get a circle going here. There we go. That's a pretty good circle. Keep it black, that's what we want the color to be. And let's say you are, or a runner or whoever, is running along this circular path. So this is like looking at a track field or what have you, from up above, like if you had a drone just right above the center. That's kind of what we're looking at here. So let's say that the diameter of the circle is 40 meters. Well, the radius is the diameter divided by 2, and 40 divided by 2 is 20 meters. So from the center outwards, this is your radius r. Okay? Now, you run with a constant velocity of 5 meters per second. 5 meters per second. And you've done 6 laps. Okay? So let's say you've done 6 laps. You've already completed that. We want to find the acceleration, the velocity, the period, the distance traveled. We can find all sorts of good stuff. Let's start with the acceleration. So because we're going along a path, we have centripetal acceleration. What centripetal acceleration points centerwards, so it would actually be, that would be our vector. So v squared over r, the velocity is 5 over your distance of 20 meters per second, sorry. That ends up being 1.25 meters per second squared. That's our centripetal acceleration. The speed, omega, we gave that equation, but omega not. The speed, omega, is v over r, which again, we can plug those in. 5 meters per second over your radius of 20 meters. Now, that ends up being 0.25 rads per second. Now, you've completed 6 laps, so let's talk about the laps a little bit. 6 laps, well, we know 1 lap is equal to what? 1 lap is just 2 pi. So instead of saying 6 laps, we can consider this just being 12 pi. So let's say we want to find the period. The period, which usually is t, is 2 pi divided by omega. So 2 pi, we just found omega, 0.25. This ends up equaling 8 pi. Going orange, I guess. If we want to find the distance traveled, we'll call that delta S. That's just your radius times your change in theta. Well, your radius, we said, is 20. And then what is the angle? Well, 12 pi. So that ends up being 240 pi. And then lastly, if we wanted to find the time it takes to do this, you can do your change in distance over your velocity. So that is just going to be 240 pi divided by 5, or 48 pi. Okay? Distance is rate times time. Just divide that over. That's all we did. So now that we did that, let's consider a few more things. So we have these different forces. We have, in this case, I want to talk mostly about the centripetal force. So the centripetal force is what's causing this centripetal acceleration. And that's because your vehicle or whatever's traveling in a circle is going to want to continue to go in a straight path. But they're not. They're going in a circle. So that requires what we call a centripetal force, and that gives us our centripetal acceleration. So the way I like to think of this is, think of Newton's second law like this. The sum of all forces inward, so I'm just going to put N, is equal to mass times your centripetal acceleration. So the force going in, whatever that force may be, is what's causing our centripetal acceleration. So the force pointing inwards towards the center of the circle. Could be other forces, could be tangential forces, what have you. But those aren't going to cause our centripetal force or our centripetal acceleration. So let's look at an example of a problem that will kind of force us to picture this a little bit better. So let's see if I can draw this. Let's start with just a good old circle. Maybe. I don't care. That can be orange, I guess. I'll do this blue. So this would be like the top-down path. In fact, let me draw a rough picture really quick first before I do this. Let's say you have some mass attached to this string of length L. It's going to trace out kind of this circular path. This distance from the center is r, and this angle theta is what's off the center. And the center is right here. Okay? Now, if we wanted to draw free body diagrams for this, first thing I would want to do is, let's draw a top-down picture. I think that tends to help. Okay? So we have this, and if you can imagine, when you're right here, which is where it was in the drawing, what force is acting inwards? Well, your tension force. Your tension force is what's doing that. There's also a force of gravity, right? But the force of gravity is not pulling it towards the center or away, it's pointing it down. So the force of gravity would go into the page if we were to think of this three-dimensionally. So just for an example, if we were to draw a free body diagram, right, you would probably say, well, we have gravity, and we have tension. Okay? And then what? This is theta. Or this is theta. That's also theta because alternating goes. This is theta. Doesn't really matter which one you use. I just prefer this one. And you could say, well, then we have t cosine theta, t sine of theta. Now, the big thing to notice here, which component of tension is pushing us inwards? That's t sine of theta, right? So this is in, this is, I guess we could say, away. This is up. this is down. So I should mention the tension that I drew here in the circle, the green bit, that's just the x component or the n component. So if we were to do a free body diagram, let's do the sum of all forces going in is equal to mass times our centripetal acceleration. Well, the only part going in is t sine of theta. So we can say t sine theta is equal to m, our centripetal acceleration. Now we also have the up and down part. So I'll just say forces, I'm going to just say, I guess, perpendicular, because they go into the page from the 3D point of view, is equal to mass times acceleration. That's not centripetal. This is 0. And we have t cosine of theta minus mg equals 0, or t cosine of theta equals mg. If I were to divide red by green, in other words, I say t sine of theta divided by, put it over here, t cosine theta mg, what do we get? Well, your tensions drop and you just get tangent theta equals your masses drop, and you get your acceleration divided by gravity. Well, our acceleration is centripetal, so let's go ahead and replace that with the equation. V squared over r. And that's what we wanted to show. You could find other things from this if you wanted, but let's try that again. But that's all that we're overly concerned about, is just kind of showing you the process on how to get there. So that's really the important thing to know, is the process. Not necessarily memorizing it, but just knowing this process will get you the answer to numerous different equations that you might have. Now, I also want to talk about when you go around in a curve. And I don't want to get too in-depth about the wheel and rolling without slipping, and if you're sliding and the difference between it. What I just want to point out is when you're driving, one sec. Sorry, someone was calling me. But anyways, okay, bank curved. So if you're going along a bank curved, this is kind of like a little, I guess, bowl, an angle theta above the horizontal. Sometimes you'll see, I can't draw a very good car. That's as good as it's gonna get. So if you're driving around this bank curve, this is like they're coming at you. If we were to draw a free body diagram for this, we know we still have gravity going down. We've talked about that. We also have a normal force pushing you up at an angle, where this is theta. Now, if we want to know, if you're going around a banked curve, so let me get my helpful shape here. If you're going around a bank curved, then it's kind of like, I don't know if you've ever seen the racetracks. I don't really watch it, but basically this bit is what it looks like. It's almost like driving through a bowl, almost. So basically the point I wanted to show was that your normal force, particularly this part of your normal force, is what's pushing you towards the center. That is your centripetal force. This is also very applicable, this concept. I just want to talk about what bank curves were. We'll get into problems here when I'm done explaining the topics. But it's also good for satellites and orbits. And that's because if you just imagine something in orbit, the inwards force is gravity. And we can't use mg because that's not what we would use in orbit. We would use Newton's law. So this is the mass of a satellite, is gravity times the mass of a planet, for example, the mass of the satellite divided by the distance between them squared is equal to the mass of the satellite times the centripetal acceleration. You can see the mass of the satellite doesn't even matter. And we know that this is v squared over r. This is v squared over r. If we multiply both sides by r, there that goes. And then we just take the square root. Velocity is g constant, the mass of the planet, divided by r square root. So we can find how fast something is orbiting. So that also is an example on where we can use centripetal acceleration. That is more or less, I think, all we want to talk about. I don't want to get into Kepler's law. We talked about weightlessness before, so that's not necessary to bring up. We might use Kepler's law sometimes. I'm going to look to see if there's any problems that go over it. If they do, we'll definitely do that, and if not, then there's no need to. But I just wanted to give you guys a quick crash course on uniform circular motion and then do problems on it. So that's what